Well, good morning. This is 9:40 actually. Sorry I'm late getting started, but I had several questions from my last class. Two different students had two different type of questions, and I had to deal with those, so I was a bit late getting those out of here. So just now getting started on this, but this is Math 125. Should be Calculus 1. There should be students in the room. I'm the only one in here. So I'll go on and get started from where we left off last time. Let me make just a couple of minor observations here. Well, some of them are not quite so minor. Let me make them all. First, I wanted to remind you, this class, Calculus 1, should be some of my best students. I have received 0 papers from any of you. So I really need those papers. Now, I have received the first test from all of you, and if any of you were here, I'd be giving those back to you today, but you're not here. Second test, I haven't received any of those, and the third test, I think, let's see, that was chapter 2, 3, yeah. The third test will be your final exam, okay? So every one of you needs to do a paper, and every one of you needs to get the second test in, and we got 1 week of class left after today. So please get these done this weekend, next week, get them to me so everything isn't piled up. It's already piled up pretty badly, but you don't have it all piled up during finals week. Don't want to go there. Okay, so that's that issue. Secondly, please do your student course evaluations. They are now open. You can do those anytime. You can wait till the end of the term if you want to, but if you're likely to forget, please don't forget. Go on and get them done sooner rather than forgetting them later. So please do those. And then the one other thing is my office hours today, as far as I know, are normal, 3:15 to 5:15. However, tomorrow, my office hours are normally 10:45 until 1:15. Unfortunately, I have a meeting with some folks that will be beginning about 11:15 and probably ending close to 1. So basically, I'll only have no more than 15 or 30 minutes available before my meeting, because I've got to get to the meeting. So it's going to be probably more like 15 minutes. And then I probably will have fewer than 15 minutes at the end, because I've got to get back from the meeting and be ready for my class at 1:15. So basically, almost no office hours tomorrow. You can catch me right at 10:45, or catch me right at 1:15, or catch me at the end of the day around 5:45. Okay. Actually, that class, I think they'll be through with their lab a bit early tomorrow, so probably 5:30, something like that. You can probably catch me then. But that class will be going until we have a lab the last 2 hours. I doubt if it'll take them much over an hour and 30 minutes to do the lab. Okay, that said, let's get going where we left off last time. We were talking about critical points. And we had just done this figure 6, which is on the top of page 212. I think we had done, yes, this was the, no, it isn't. I don't know. I guess we had not done, yes, we had. Let me see. Yeah, we had done example 3. This is a figure for example 3. Got it. So now we're going to move to testing critical points. Okay? I'm going to close the door because, yeah, it is. All right, sorry about that. I left the door open thinking students may be coming in, but since none of you are here, no reason for me to be yelling down the hallway interrupting other classes. There is a useful test for determining whether a critical point is a minimum or a maximum, or neither, based on the sign change of the derivative at that value. Okay? To explain the term sign change, suppose that a function g satisfies g of c is equal to 0. So c being your critical point. Okay? If the function satisfies that, g of c is equal to 0, we say that g of x changes from positive to negative at x equals c. If g of x is greater than 0 to the left, and g of x is less than 0 at the right of c, for x within a small interval around c. Boy, that's a lot of words, and I'm not even sure they stated it right. They did. It changes from positive to negative. If g of c is equal to 0, and anything to the left of that, if it's a positive and to the right, it's negative, or if from the left it's negative and to the right positive. If it changed sign, then it changes from positive to negative or negative to positive. Okay. Pretty obvious, I think. A sign change from negative to positive is defined similarly. Okay. And here's the figure. Here at x equal 1, obviously your function f of x, y is equal to capital F of x here. At x equal 1, the f is 0. At x equal 3, it's 0. And at x equal 5, it's 0. Okay. At x equal 1, to the left of 1, it's positive. To the right of 1, it's negative. So you have a sign change there from positive to negative. At x equal 3, to the left of 3, the function is negative. To the right is positive. So you have a sign change there from negative to positive. At 5, however, to the left of 5, it's positive. To the right of 5, it's positive. That means there's no sign change. And since it's positive on either side, 0 at 5, that must be a minimum. Okay? So, here is Theorem 3, the first derivative test for critical points. Okay? Assume that f of x is differentiable, and let c be a critical point of f of x. Okay, that is a differentiable function. I think someone's coming in. Yes, okay. And I'm so glad you're here. Okay? Yes, I did. Thank you. Now, do you go by Kim or Nicole? Okay. Because I noticed the last two things I've noticed that you had signed were Kim, but I thought you told me the first of the term you went by Nicole. So.
I just
okay.
But I didn't think that this would take that long. It was like an ACT test.
Yeah, right, exactly. I didn't know that's what you were doing, the CAP test, I guess it's called.
Yeah, they don't say CAP, ACT test.
Yeah.
It's an ACT test.
Yeah, I think put out by that same company, right? And there are 3 40-minute parts. And that's 120 minutes. That's 2 hours, and then with some instructions at the beginning and in between the two sections. Yeah. Where was it given? Here on this campus?
It was given
in the testing room. Yeah.
It was given at Birmingham, but it was given here.
It's oh yeah, I'm not even. Yeah. All righty. Well, I've recorded it and it's there. Let me put it on the projector now so you can see what we're talking about. And let me just quickly go over the 3 major announcements I did. They're not that major. Number 1, they have open student course evaluations, so please do those. You can wait till the end of the term if you want to, but just don't forget. Better to do them early and not forget than to put them off and then forget. Yeah. So, as we were saying, the first derivative test for critical points assume f is differentiable and c is a critical point of f of x. So you already know how to get the critical points. That's where your first derivatives is 0 or undefined. Okay. So, what we're looking at now is f prime of x. Okay? The first derivative of f. Remember, we said it was a differentiable function, so you can take the derivative. Do that. You found the critical points. So look at f prime of x, and if f prime of x changes from positive, in other words, is going upward to the left of c and then going downward past c, it's 0 at c, or it's undefined at c, then that makes f a local maximum. If the first derivative is positive to the left of c, negative to the right of c, where c is a critical point, then that makes the function f of c at that point a local maximum. If, on the other hand, f prime of c is negative to the left of c, positive to the right of c, that means it's going down to the left of c, going up to the right of c, then that makes f a local minimum, f of c a local minimum. Now, there is another possibility. What if it doesn't change at c? It's either positive coming in and positive going out, or negative coming in and negative going out, past c. Then what you have is called we'll get to the term later, but we'll call it a point of inflection at x equals c. That isn't a maximum or a minimum. It's a neither. All right, the second announcement I was going to tell you about is that while my office hours are good today, 3:15 to 5:15, tomorrow, normally they're 10:45 until 1:15, because normally I eat on campus. But I've got to meet some people tomorrow, and I'm in a meeting with them, and it's going to be off campus. So I will be leaving campus probably around 11ish, okay, because we're meeting at 11:15, and the meeting's probably going to go to close to 1. I'm going to book it back here for my 1:15 class. So I won't have many. If you catch me right at 10:45 tomorrow or right before 1:15, you can catch me either of those times. Or, I was saying before, my physical science class has a lab tomorrow afternoon from 3:45 to 5:45. However, I don't think they'll be in lab for much more than an hour to an hour and a half. So sometime before 5:45, I'm available too. So, but just look for me. Yeah. Okay. Is that all of them? The student course evaluation, my office hours, and seemed like there was another one. I don't remember what it is now. Okay. If I think of it, I'll tell you. I think I said it earlier so listen to YouTube when it comes up. All right, we're just doing the first derivative test for critical points. Do you remember how you find critical points? At first? Okay. First, f of x has to be a differentiable function. Okay? If it's not, you can't even mess with it. But if it is a differentiable function, then take a derivative and set the derivative equal to 0. Any place where the first derivative is equal to 0, that's a critical point. Or any place where the first derivative is undefined, that's also a critical point. So when you have that first derivative, if there's any value x that makes that undefined, like is 0 in the denominator, or negative in a square root, or negative logarithm, or 0 logarithm, anything that makes it undefined, that's a critical point. And the other one is where the first derivative is 0. So where the first derivative is undefined, and the first derivative is 0. Those are your critical points. Now, also continue looking at that first derivative. Look just to the left of the critical point, okay? and see if what the sign of that first derivative is. If the first derivative is positive coming up to the critical point, 0 at the critical point, and is negative after the critical point, that makes it a maximum. If it's negative coming into the critical point, 0 at the critical point, and then positive afterwards, that makes it a minimum. Now, I said 0 at it. If it's coming up and is undefined at the critical point, but positive on the left-hand side and negative on the right-hand side, that's a maximum. Positive on the, negative on the left-hand side, undefined at the critical point, and then positive after that, that makes it a minimum. But if you have a situation that it's undefined here, undefined there, but it's positive going in, positive going out, then it's neither. We'll call that later something like an inflection point or something like that, but it's a neither maximum or minimum. You can also have a situation where it comes up as 0 here, but then goes out and keeps going up. Positive on the left, positive on the right, that's a neither. Negative on the left, 0, then negative on the right, that's a neither. Okay, neither maximum or minimum. Those are points of inflection. Okay. But we haven't gotten there yet. I'm just telling you ahead of time. Okay, so here would be your, if this is your function, let's see, is this an example? Yeah, this is example 4, I think it is. I'll blow it up to begin with. Okay, here's a function, f of x is equal to x cubed minus 27x minus 20. Okay, there's your function. Okay, first thing you would do, take a derivative. What's the derivative of f of x? Derivative of f of x. Take the derivative of that. Remember your power rule? 3 times the coefficient, exponent times the coefficient, and drop the exponent by 1. So 3 squared. Right, you drop that by 1. 3x squared minus 27. You get nothing there. Okay? Now 3x minus 27, that's defined everywhere. So there's no place that first derivative is undefined. But the next thing you do, set it equal to 0. 3x squared minus 27 is equal to 0. Well, divide everything by 3. That gives you x squared minus 9 is equal to 0, right? What values of x will give you zeros there? X squared minus 9 equals 0. X squared equal 9, which would be x equal either positive 3 or negative 3. So those are your two critical points. X equal positive 3, x equal negative 3. Okay? So x equal positive 3, but here's a positive 3. If you drew the graph, that's the local minimum, that one's the local maximum. Okay? Your derivative is 0 at both places. Okay? But if you plotted the f prime, you see at x equal negative 3, your positive to the left, negative to the right, that made that a local maximum. Negative to the left, positive to the right, that would mean a local minimum. Okay. Now, this is not this problem. This is another. What if you have a place that's positive to the right? The first derivative is positive, 0, critical point, but positive after that, either local minimum or local maximum. Call that an inflection. And if you did the plot of this one, you would have positive to the left, 0, and then positive to the right, slope to slope, then that's this is cheating a little bit, but here the second derivative is 0. The second derivative is 0. That doesn't always mean, but it could mean that you have a point of inflection. Doesn't always, but it could. Okay. So, I jumped ahead with the second derivative there. All right, I think example 5 is next, and I don't think we have, oh no, they have this little table next, okay? This is example 4 still, okay? We're looking at f of x by evaluating the sign of f prime of x, okay? So if f prime of x is positive, that means the first derivative is increasing, okay? If f prime of x is negative, that means it's decreasing. That meant that had to be a maximum in between. If f prime is negative, that's between -3 and 3 it is, and at 3 it's 0 again, but to the right of 3 is positive, that meant it's a local minimum. So you can look at your sign of f prime and then determine what if your critical points are either maximum, minimum, or neither. All right. So now I think we're ready for example 5. Okay. This is part of it, but this is further on. Let's do example 5. Analyze the critical points and the increase-decrease behavior of f of x. Let me get my pen activated here. F of x is equal to cosine squared x. Seems like we've had this one before, plus sine x. And we want this on the interval from 0 to pi. Only interested in that interval. Okay? Analyze the critical points and the increase-decrease behavior of f, that f, at that. So, what's the first thing we got to do? Take a derivative. So f prime of x is equal to okay. All right. Now this is a composite function. It's the square of a trig function. So do the outer function first. The squaring function would be 2 times cosine x to the first power. That's the power function. Chain rule, then multiply that by derivative of cosine, which is minus sine. Okay? So that's the derivative of the first part. Plus, what's the derivative of sine? Derivative of sine is? It is cosine. Okay? I wanted you to say cosine. Okay. It's cosine x. Okay, there we took a derivative. What do we do with that derivative? Okay, say that again. Either where it's undefined or equal to 0. Well, the sines and cosines are defined everywhere. There's no place they're not defined, so therefore there's no place that first derivative is undefined. Fine. So now we set it equal to 0. These would be the other values of your critical point. Okay? So what do you do with that equation? I'll rewrite it ever so slightly. Minus 2 sine x cosine x plus cosine x equals 0. What would you do with that? Well, you could, but you didn't have a 1/2 cosine x, so that won't help you a lot. Okay, let's factor out a cosine. Factor out a cosine. So that gives you cosine x times a minus sine x. Second? Yeah, minus 2 sine x plus 1 equals 0. Okay, good deal. Now what do you do? Okay, now let's set each of them. Here you have a product of two entities equals 0. Set them both equal to 0. So this implies that either cosine x is equal to 0 or minus 2 sine x plus 1 is equal to 0. Okay, cosine x equals 0. Where, when x is between 0 and pi, where is cosine x equal to 0? Yeah, between 0 and pi, x between 0 and pi, is there any place there where cosine x is equal to 0? Where is the cosine equal to 0? At pi over 2. So this one would yield you a x equal pi halves. There's also 0 at 3 halves pi, but that's outside that. At negative pi, that's outside that. So that's the only value in between 0 and pi where cosine is equal to 0. Now let's work with the other side, the other equation. What would you do to solve that one? Okay.
I would divide by -2.
Okay. Sine x is equal to negative 1/2. Not quite. Because you had a negative 1 there, you divide it by negative 2. That gives you plus 1/2, doesn't it? Okay, plus 1/2. Okay, where in between 0 and pi is sine of x equal to 1/2? Pi over 3 is root 3 over 2.
Okay, so it's pi over 6.
6, pi 6, exactly. So that's one value. X equal pi 6 is 1/2. Any others between 0 and pi?
Well, yes.
Okay. 5 over 6, exactly. Same, what do they call that? Reference angle, pi 6, but it's pi 6 short, okay. Or 5 pi over 6. So there are 3 candidates between 0 and pi where the first derivative is 0, okay? Now, so pi 6, pi halves, and 5 pi 6. All right. Now, what we have to do here is, analyze the critical points. We found the 3 of them, and the increase-decrease behavior of f of this function in that range. So it said first find the critical points. We did. Okay. And now we determine what it's doing on any side. Now, you can do it several ways. Okay. Remember, 0 wasn't included in here, but cosine of 0 would be 1, and sine of 0 would be 0. So neither one of those would produce a 0 for you. So what we can either do, and 6 of one, half dozen of the other, I think most of the time it's helpful to consider the derivative function, okay? So if you put in something between 0 and pi 6, do you have a favorite number between 0 and pi 6? Remember, pi is about 3.14, and 6 is 6, so it's a little bit more than 1/2, right? So they suggest using f prime of 0.5. So plug in this value, but put in a 0.5 there. -2 times sine of 0.5. Be sure you're in radian mode. You're not in degree mode. Okay, -2 times the sine of 0.5 times the cosine of 0.5 plus the cosine of 0.5. Okay, it might actually be a little easier to do this one. Cosine of 0.5 times, open parentheses, -2 times sine of 0.5 plus 1, close parentheses. See what you get. You get a positive value. That means the function is increasing to the left of pi 6. Okay, getting close to 0, 0 at pi 6. Well, let's pick a point between pi 6 and pi halves. The pi 6 is a little bit more than 1/2, and pi halves is a little bit more than 3/2 pi. So, I'm sorry, pi halves is a little bit more than 3/2. That's what I'm going to say, 3/2, 1 1/2. So how about 1? 1 is in between 1/2 and 3/2. So let's do f prime of 1. Again, plugging in here, cosine of 1, be sure you're in radian mode. Cosine of 1 times -2 times sine of 1 plus 1, and see what you get there. And Rodney decided to grace us with his presence. Good. All right. All right. And according to them, when you do that, you'll find out f of 1 is -3.37. So that means to the left of pi 6 is an increasing function. To the right of pi 6 is a decreasing function. Guess what? Pi 6 is a relative maximum. Gotta be, right? So the behavior of f of x is it's a maximum. Okay? Now, we've already determined that at 1 it's a negative number. So in between 3/2 and, let's see, 5 times 3 would be 15, 6. That would be 5/2. Okay? So in between 1 1/2 and 2 1/2 is 2. So let's use 2. So be sure you're in radian mode. Cosine of 2 times, open parentheses, -2 times sine of 2 plus 1, close parentheses. They come up with a 0.34, positive value. So that means the first derivative was decreasing, was negative, meaning the function was decreasing to the left of pi halves, increasing past pi halves. That means a relative minimum. Okay? So that means here is a relative minimum at pi halves. I don't like their little tables. I'll just tell you, I don't like them. It's so much easier to just think through it and see what's happening. The behavior of f of x, it's up here, down here, that's positive, negative, yeah, positive, negative. If the derivative is positive, then the function is increasing, negative is decreasing, positive is increasing, negative is decreasing. Here we have f of, again we said this was 5 halves, okay? So that would be something greater than 2 1/2. This is 3, so between 2 1/2 and 3, and this is a little bit more than 3, they just use 3, okay? And when you plug in there, your first derivative of 3, cosine of 3, times open parenthesis -2 times sine of 3 plus 1. Be sure you're in radian mode. You find out it's negative again. If the derivative is negative, that means the function is decreasing. So here you have increasing, decreasing relative maximum, decreasing, increasing relative minimum, increasing, decreasing relative maximum. Okay, so you can determine what each of those are. The behavior changes sign. The first derivative changes sign in between each of those critical points and between the interval, left-hand interval and right-hand interval. That's the other thing to consider. Okay. Here, I think, is the figure for that one. Okay? All right, here's the function y is equal to f of x. This was the cosine squared x plus sine x. Okay? But we're only interested from 0 to pi. Okay? We're not interested out here or over here. Okay? 0 to pi. First derivative tells you, the first derivative is defined everywhere, no sweat. It's equal to 0 here, here, and there. Okay? The function first derivative is positive to the left of this, and they use the 0.5 here. It's negative to the right of that, they use the point pi thirds would be in between these, so that would be about 1. Here they use the 0.2, increasing there, and here they use the 0.3, decreasing there. So increasing, decreasing, maximum, decreasing, increasing, minimum, increasing, decreasing, maximum. Now here they plotted these first derivatives. Not necessary, but you can certainly do it. The first derivative here was positive, but it's decreasing. So here it's a positive number, but decreasing. Here it's 0. Here it's a negative number because it's decreasing still. So a negative number here until it reaches back to 0 again. And then it's positive again from here to there, and then negative from there on. So that tells you it's 0 here, here, and here. Change the sign here, change the sign there, change the sign there. So it's, and these are indicating the signs on the first derivative. Positive here, negative here, positive there, negative there. So if it goes from being positive to negative, that means a relative maximum. From negative to positive, that means a relative minimum. Positive to negative, that means a relative maximum. My contention is they almost overanalyze it. Okay. But that was figure 9. That's example 5, I believe it was. Okay. Let's see if they have anything for 6. Okay. Here is your function. Analyze the critical points of f of x equal 1/3 x cubed minus x squared plus x. What you reckon the first thing you're going to do to that is? You're analyzing the critical points. You got to find the critical points. And how do you do that? the title of this chapter? Applications of the derivative. So in other words, take a derivative. So what's your f prime of x? You tell me. Say again. Okay. Now take a derivative of this function right here. What's the derivative of that first term? Exponent times the coefficient and drop the exponent by 1. 1x squared, yeah. Or just x squared. Okay? Next term. Minus 2x. 2 times the minus 1 is minus 2. And reduce it by 1. Next. Plus 1. Got it. Okay. And then the two things you ask yourself. First, is there any place where that derivative is undefined? No, that's a polynomial function. It's defined everywhere. So there's no place it's going to be undefined. So what's the next thing you consider? Where it's equal to 0. The two places where your critical points could be where your first derivative is undefined or where the first derivative is 0. That's what you're looking for. That was defined everywhere, so there's no places it's undefined, so then we set it equal to 0. Now what does that give us? Factor it. What does that give you? X and x. Say again? No, you got to have some things that multiply to be 1. Okay. Now here's my probably silly way of doing factoring. Unfoil. Okay. So you know it's got to be. We hope it's going to be 2 binomial factors. Obvious choice has got the only possible factorization of x squared is x times x, right? Next place you look is the sign of the last term. What is it? Positive. What does that tell you about these two signs? No, they've got to be the same. They could be positive, but they've got to be the same. See, a minus times minus would be a plus, or plus times plus would be a plus. It's just got to be the same. Plus times minus would be minus. Minus times plus would be minus. So they've got to be the same. So they're either both pluses or both negatives, right? You look at the middle term, and what's it? Negative, so that means these two have to be negative. So minus, minus. Okay, and then you look at the last term. What's the only possible factorization for 1? 1 times 1. Okay? Now, I don't know if that's the factorization. I do, but how we check it? Boil it and see if it is. X times x is x squared. Got it? Minus x is minus 2x. Got it? Minus 1 times minus 1 plus 1. Yes, that's the factorization. Okay? So, this means either x minus 1 is equal to 0 or x minus 1 is equal to 0. Guess what both of those yield? X equal 1. Add 1 to both sides. Over here, x equal 1. So, you have a double root there. You have only one place that's your critical point, x equal 1. And so what we have to do is figure out what the first derivative is doing near x equal 1. To the left and to the right. Okay? Well, to the left of x equals 1, let's use x equals 0. Okay? And we put 0 here, 0 here, you get a 1. So it's positive to the right of 1. Okay? At 1 is equal to 0, we know that. To the left of 1 is positive. To the right of 1, though, like at 2, plug it in here. You get 2 squared minus 2 times 2, that would be 4 minus 4 equals 0 plus 1 is 1. So to the right of 0, to the right of 1, it's also positive. So it's positive here, positive there. That means it's neither a maximum or a minimum. Looked like it's going to be a maximum, but then it looked like it's going to be a minimum. It was neither one. Okay? And that's what it's showing here. Now this is your first derivative is equal to 0. The first derivative to the left of this is positive. To the right of that is positive. So it's not going to be either a minimum or a maximum. It's what we call a point of inflection. Okay? Does that make sense? Okay. And that's what we got. Neither local min or local max. All right. Now, my slide set is skipping a figure here. Okay? This is example 7. So we don't have example 7 on the slide, so I'll do it here. Analyze the critical points of this. F of x is equal to 1 minus x to the 2/3 power. Okay. What do you reckon you're going to do first? Take a derivative, exactly. So your f prime of x is going to be what? Two over 3, right? 2 over 3 times 1 minus, I'm sorry, I can't talk. Okay, 1 minus x to the negative 1 over 3, right? You're subtracting 1 from 2/3 and you get negative 1/3. Okay. You have one more little step here to do. You want to know what it is? Chain rule. Times the derivative of the inner function. And what's the derivative of the inner function? Anyone know what the derivative of the inner function is? Here's the inner function. What's this derivative? So again, it doesn't have an exponent, but it does have a coefficient. Well, it does have an exponent, you just don't see it. It's understood to be 1. And it has a coefficient of -1. So what's this derivative? Negative 1. Not x. Negative 1. Negative 1, 1 times negative 1 is negative 1 times x to the 0 power is 1. So that's just a negative 1. Okay? If that was your function to begin with, I said take the derivative, what would it be? Derivative of this is 0, derivative of that is -1. -1. minus sign. Okay. So then you have the one more minus out here. Calls the derivative of the inner function. All right. Now, I'm going to rewrite this ever so slightly. Okay? And here's how I'm going to rewrite it. I'm going to put the minus out front. 2 is in the numerator. 3 is in the denominator. And bringing this down, this is going to be the cube root of 1 minus x. So that's going to be 1 minus x to the 1/3 power. That's an ugly 3. Okay. Okay. Now, what 2 questions do you ask yourself? What do you do with the first derivative once you get it? That is the first derivative. Okay. Two questions do you ask yourself about first derivatives? Second? Where is it undefined? Is that undefined anywhere? Okay. Okay. What can you never do with the denominator? What can your denominator never be? 0. You can't ever divide by 0. Is there any value for x that would make that denominator become a 0? Yes, x equal 1 is undefined. Okay? So that's what we do. X equal 1, the f prime of 1 undefined. Okay? So there's a critical point. X equal 1 is a critical point. Okay? Now, the next question you ask yourself, is there any place where that derivative can be 0? Well, if you have a fractional form, the only way you can have the fractional form being 0 is if the numerator is 0. Can 2 ever be 0? No. Okay? Negative 2 can never be 0. No. So our only critical point is where your first derivative is undefined, and that's where x equals 1. Okay? Now, what you ask yourself here is pick a point a little to the left and a little to the right and see what happens. Okay? So let's do, at 1 it's undefined, let's do f prime at 0 and see what we get. Let's use this form here. This would be minus 2 over 3 times, when x is 0, that would be 1 to the 1/3 power. Well, guess what? Cube root of 1 is? Cube root of 1 is 1, so that would be negative 2/3, right? So this would be negative 2/3. So it's a negative first derivative to the left of 1. So that means it's going downhill, right? At 1, it's undefined. Let's pick up to the right of 1. How about 2? So let's do 2. F prime of 2 would then be minus 2 over 3 times 1 minus 2 would be negative 1. The cube root of negative 1. Anyone want to know the cube root of negative 1? Is it defined? Can you take cube roots of negative numbers? Yes, you can. You can't take square roots of negative numbers or any even root of a negative number, but as long as this is an odd number, yeah, you can do that. And the cube root of -1 is -1. So then that would make this a 2/3. Okay, because let's just take, what is -1 squared? 1. Okay, can you square any number and get it to be a negative number? No, you can't. So therefore, if you had a negative number, there's no way you can take a square root of it, right? But let's do -1 cubed. And what's that? -1, because it's an odd number. So therefore, you could take the cube root of this and get that. Yeah, you can do that. You can't take the square root of this and get that, because the square root of 1, yeah. I mean, no, if this were a -1, you can't take the square root of that and get that, because there is no number that you can do it squared to give you -1. It just doesn't exactly. Okay? So this would give you then 2/3. Well, what does that mean? That means your function is increasing to the right of 1. Decreasing to the left of 1, increasing to the right of 1. What does that mean? Is it 1? Decreasing to the left, increasing to the right. That means at 1 it's a minimum value. Okay? Now, if you got your text, I don't see either one of you do, your figure 11 in your book, that's not the same as figure 11 on the slide, that shows you that function. And here's how it looks. It comes in like this and goes out like that. Okay? Here the derivative is undefined because it's negative infinity coming this way, positive infinity going that way. Undefined derivative. Okay? But it's negative coming in, positive going out, makes it a minimum. That's called a cusp, by the way. All right. Now, the last little thing in this section is a proof of the mean value theorem. Okay? And they use this slide, so I'm going to erase what we've got here. Any questions on example 7? The only critical point is x equal 1, and that's because the first derivative is undefined there. There's no place the first derivative is 0. And then we test it by a point to the left of 1 and right of 1, 0 and 2, to see what the first derivative is. Negative to the left, positive to the right means it's decreasing this way, increasing that way, making x equal 1, the critical point, a relative minimum. Okay. So I think I will erase everything on the slide and blow up this part. Okay. Oh man. This is your proof of the mean value theorem, which you don't have to do, but let me just give you the quick and dirty on it. Okay? Here's your value when x equal a, x equal b. Here's f of a, there's f of b. They're not equal to each other, which means the slope of the secant line between f equal a and f equal b is slope. In this case, it happens to be a positive slope. If they were the same values, the slope would be 0. This is not, so m is a number, in this case, happens to be greater than 0. Now, excuse me, g of x is the vertical distance between the graph and the secant line. When x equal a, of course, is that 0, when x equal b is 0. But anything between a and b, this graph is going to be some positive value. The distance between the graph and the secant line is some positive value. Okay. What they're going to do is take this function, which is the difference between f of x and the secant line, which is mx plus r, whatever that happens to be, then that's going to be your g of x. What you want to do is maximize that. Here's the minimum, there's the minimum, so somewhere in between there is the maximum. And where that's the maximum value, then that's where your slope is going to be equal to this. And that basically gives you the mean value theorem. Don't want to go into gory detail about it, but that's what you get. All right, now, question here. This is in the summary, same type thing we did before. I'll blow it up again. This is just going on before. If you study the function, the first root of the function at each of the critical points, look to the left and to the right. If it's positive coming up to the critical point, negative going past the critical point, the first derivative, that means it's a maximum. If it's negative coming toward the critical point, positive after the critical point, that means it's the local minimum. If it's positive coming towards 0 at the critical point and then positive afterwards, not. Negative coming in 0 at the critical point and negative afterwards, not. Neither a minimum or a maximum. Now, you also have your, I said zeros there for your first derivative. If you're positive coming in, and then it becomes undefined, and undefined to negative, that means it's a relative maximum too, but it's not a your derivative is a 0 there, it's undefined. And if it's negative coming in, but it's undefined but positive going out, that means it's a relative minimum, even when the derivative is not defined. Okay. And that ends the slide set. Do you want to do preliminary questions? Do you find them helpful, or do you rather move on? It's up to you. Do them or not. Preliminary questions. Say not. Yes? If you want them, we'll do them.
They're in the book, right?
Yeah, they're in the book.
I will do them on my own.
You will do them on your own. The answers to all of them are in the back, so, or most of the time they are. Okay? So homework exercises will be any of the odds, 1 through 7, either 9 or 11, or both. 13 says you need a graphing utility. If you do, use it, but if you don't, see if you can do it on your own. Any of the odds, 15 through either 15 or 17 or both, either 19 or 21 or both, either 23 or 25 or both, and any of the odds 27 through 57. Quite a few of those. Okay? Any of the odds 59 through 71. Okay? And then I'll let you decide whether you want to do any of the further insights and challenges. That would be 73 through 81. You don't have to do any of those. All right, let's move away from this then and to the next section, which is 4.4. I'll try to do this pretty quickly, okay? If it'll open, I'll do it quickly. I'm sorry? Oh, number of people you can bring? Yeah, I think it's it's held in the Birmingham Jefferson County Civic Center. It's an East Meeting Room or somewhere like that, which is a pretty big room, but there are sometimes it's standing room only and they have to open some more doors and get some more chairs in there. So I would say if you are bringing a good sized crowd, encourage them to get there a little on the early side so they can get a seat. They'll manage to see everybody, but sometimes they have a delay before they get it done because the Civic Center responds sort of slowly as there's a crowd. They do respond, but I just say get there early if you think you got a big crowd coming. We had an international student, an Italian kid who lived with us his senior year of high school. He was an American citizen, but his family had moved back to Italy. They wanted him to be able to go to school, college in either country. So they thought it would be better if he came to the U.S. and graduated from a U.S. high school. So he lived with us. We're friends with his family. So he lived with us that year and graduated, did very well too. Then he went back to Italy. They have 5 years of high school, so he graduated there too. And then he applied to schools in the U.S. and was accepted at Harvard. Now, he had a full-ride scholarship at University of North Carolina, which we all thought he ought to go for, but he wanted to go to Harvard. So he cost his family their home. I think, yeah, they had to sell the house to pay for Harvard. And he went to Harvard, but they only allowed 4 guests for their graduation. And his dad couldn't come, so his mom came over from Italy. My wife and I went, and my wife has a niece who was not his age, but close to his age, and good friends with him. She had known him when he was here, so she came with us. So that you were limited to 4 at Harvard. Here, not. Okay. So, what's that? They moved to an apartment, a flat, because it cost so much for him to pay for Harvard. And he had a full ride scholarship to a great school, University of North Carolina, but he chose Harvard. Not on our recommendation, but what's that? I know, but you see, young kids sometimes don't think long run; they think what they want right then, Okay, that's enough of that. But they did limit to 4, and we don't. Okay. Now, let's look at some concepts. This is 4.4. Let's just give you an idea of some shapes here. Anytime something is curving upward, we call that concave up. That's certainly curving upward. That's curving upward. That's curving upward. All those are concave up. Okay? Concave down is when it's curving downward. Okay? Concave down, concave down, concave down. In other words, the center of the curve for a concave up is above the curve. And the center of the curve for concave down is below the curve. Find the center of that curve. The place where you put your compass to draw that curve, that would make it. So that's what we mean by concave up and concave down. Why are we doing this in calculus? Well, we're going to refer to that in this section. Okay? Now let's look at these curves. What would you tell me about the first derivative of this curve here? First, tell me a sign, positive or negative? Negative. And it's a pretty large negative number or a small negative number? Fairly large. Down here, it's still negative, but getting less negative, right? Less negative. Here it's 0. Okay? Because it's horizontal here. Here it's slightly positive, but very small positive number. larger positive number, larger positive number, larger positive number. So guess what? The first derivative is always increasing here, right? Very negative, less negative, less negative, 0, slightly positive, more positive, more positive. The first derivative is increasing. Here, slightly positive, more positive, more positive, more positive, increasing here too. Slightly or very negative, less negative, less negative, less negative, still it's increasing. So if your first derivative, whether it's negative or positive, if the first derivative is increasing, then it's concave up. Let's look at this one. First derivative is positive and fairly positive, but here it's less positive, less positive, less positive, 0. Slightly negative, more negative, more negative, negative. So every place here, the first derivative is decreasing. Whether it's positive or negative, it's still decreasing. So that's concave down. Slightly negative, more negative, concave down, decreasing. Slightly positive, somewhat positive, less positive, decreasing here too. So if the first derivative, whether it's positive or negative, is increasing, it's concave up, decreasing, it's concave down. That's what the next slide shows you. Okay? I wanted you to see it first before you saw what they did. Okay? So here the slopes of the tangent lines are increasing. Negative here, 0 there, positive there. Slopes increasing, so therefore it's a concave up. Here, the slope is positive, 0, negative, so the slopes are decreasing, concave down. Okay? Exactly like we said before. Okay? Now, here's your definition of concavity, I guess is how you say it. Okay? Let f of x be a differentiable function. It's not differentiable, there's not much we can do with it. Okay? So let it be a differentiable function on some open interval, a to b. Then f is concave up on a to b if f prime is increasing everywhere on a to b. It's concave down on a to b if f prime is decreasing everywhere on a to b. Okay, next question. Let's go back to the function f. How do you tell if f is increasing? It has nothing to do with concavity. How do you tell if f is increasing? The first derivative is positive, right? Agreed? The first derivative is positive, it's an increasing function, right? How do you tell if it's decreasing? The first derivative is negative, okay? And if it's 0, that means that's a critical point. It's changing. It's increasing, decreasing, or it could be, okay? So, if we're interested in whether f prime is increasing or decreasing, what do you think we're going to do to that? Take the derivative of f prime. That would give you f double prime. If f double prime is positive, then f prime is increasing. If f double prime is negative, that means f prime is decreasing. So there's another test for concavity. I may have jumped a little bit ahead, but here's what we have. Oh, this I think, I'm sorry, I probably did jump way ahead. This is example 1. Stocks of 2 companies, Aeronaut Industries and Blurbenthal Business Associates, AI and BBA, went up in value. Okay? Here's company A, company B. They're both increasing. Which one would you want to invest in? Company B. But wait a minute, this one's increasing quite rapidly here. This one's just barely increasing here. But this one's concave up, that one's concave down. It looks like it's about to reach a max, start heading downhill. This one, sure, it can't go up forever, but it looks like it's trending very nicely. So I agree. Okay, with time, yeah, I would go with that. And what we do, we look at the derivatives. Now, back when the stock market, remember before its crash, y'all were maybe too young to remember that, you heard a lot of people talking about derivatives. I thought, oh, finally these investors are making some sense. They're not just looking at whether it's increasing or decreasing, they're looking at the rate of the increase. I thought that's what they meant by derivatives. It wasn't. They were looking at something else. If they had been doing that, that would have been worth looking at. Okay? So there's example 1. Here is, they're beating this to death, aren't they? Okay. Another function, what the blue line, the blue curve is y is equal to f of x. This function is a decreasing function, but what can you tell me about its concavity? What would you tell me about its concavity? No, but it's concave up. It's a decreasing function, but the rate of decrease is getting less and less and less, meaning the first derivative is increasing. It's a negative, a negative, a negative, but it's getting less negative all the time, meaning it's increasing. Like -3, -2, -1, that's still increasing. Okay? So that's concave up. Okay? How can you tell? Find the center of curvature of this. It's above the function. Concave up, it's pulling it up. So that function is a decreasing function, but its derivative, even though the derivative is negative, is still increasing, getting less negative all the time, so it's a concave up function. Okay? Now, here's a test for concavity. I want to say concativity, but that's not really a word. Ew, yuck. Okay. And it's what I hinted at you just a moment ago. I wasn't getting too far ahead. Here's the test for concavity. Assume that f double prime exists for all x's on the interval a to b. If the second derivative is positive, meaning first derivative is increasing, that means it's concave up. If the second derivative is negative, that means it's concave down. So rather than thinking of the first derivative as increasing or decreasing, all you have to do is take the second derivative. This is plus concave up minus concave down. Pretty simple and straightforward, right? Okay. Let's look at a few. Again, we're just looking at it. What would you tell me? This one? Concave down, what can you tell me about the second derivative? Negative. Yeah, negative is down. That one's concave up. Okay? Now, put those two together and you've got a curve like this. Here we have concave down, here we have concave up. Somewhere in between, it changes concavity. This one, the second derivative is negative. Here's the second derivative is positive. That tells you right in there the second derivative must be 0. So that is a point of inflection. Another point of inflection. I used the term earlier. This is another case of a point of inflection. Okay? So, here's theorem 2, your test for points of inflection. Okay? Assume that the second derivative does exist. Okay? doesn't, you really can't test. So, if the second derivative at a critical point, well, let's see, is that a critical point now? No, it's not necessarily a critical point. At some point C, earlier that was critical point, now it's not. If the second derivative at some value C is equal to 0, and f double prime changes sign at C, in other words, it was positive going in, negative going out, then that is f has a point of inflection at x equals C. If the second derivative changes sign there, okay? So, here, concave down, concave up, the second derivative is 0 there, but it's negative coming in, positive going out. That's a point of inflection. Okay. Now, all right. Here's a function. Let's see, is this an example? Yeah, this is example 3, I think. No. Example 2, maybe. Find the points of inflection of f of x equal cosine x. Yeah, there it is. F of x equal cosine x on the interval 0 to 2 pi. Here's cosine x. Starts at 1. 0 at pi halves, minus 1 at pi, 0 at 3 halves pi, and 1 at 2 pi. Okay? Now, what you may be interested in there, I'm going to take it full ride here. There's your function. Guess what one of the first things we're going to do? Take a derivative of that function, right? Gotta get my pen back. Okay. Oh, yeah. So if f of x is equal to cosine x, what's f prime of x? Anyone know? Help me. What's the derivative of cosine? Second? No. Minus sine. Derivative of sine is cosine, derivative of cosine is minus sine. Now here's one way I remember that. Look at the curve. Okay? Derivative at 1, at 0 I mean, is 0. Derivative is 0. The tangent line is 0 here. Well, that's what sine of 0 is 0. But here the derivative is negative. The sine, though, is positive, so that makes it a minus sign. So anyway, here is your curve. F of x is that. The first derivative is minus sine x. So in the first quadrant, from 0 to pi halves, sine is positive, but the derivative of cosine is negative. Okay. Downhill there. Okay. So that's it. Now, the question here is find the points of inflection. Well, the point of inflection is what? Where the second derivative. So do the second derivative of x. And what would that be? Just told you what the derivative of sine was, didn't I? Yeah, we did derivative of cosine, but I happened to mention what the derivative of sine was. You remember what it was? Derivative of sine is cosine. derivative of cosine is minus sine. So this derivative of this would be a minus derivative of sine is cosine. Okay, so there's your second derivative. Okay? Now, your points of inflection, that's what we're looking for. Find the points of inflection. What are they? Where the second derivative is 0. So set this equal to 0. And where is cosine equal to 0? Somewhere between 0 and 2 pi. Where is the cosine equal to 0? Pi halves and 3 halves pi. All the half pi's cosine is 0. So here it's 0, there it's 0. That means on the original function, that's an inflection point. You think it is? What's the concavity of this one? Where's that bending? Downward. That's concave. Down. What's this one? Concave up. So sure enough, that's an inflection point. Just the fact that the concavity is equal to 0 isn't enough. It's got to change signs on either side. It's negative here, positive there, so therefore that is a point of inflection. Okay, here the concavity is up, there's the concavity is down, so the 3 halves pi is also a point of inflection. The second derivative is positive here, negative there, so therefore it's positive, negative, meaning concave. That is a point of inflection. Okay? Because it does change sides. It's 0, but it changes sides on both sides. Okay. This is example 3, I think. Okay? Find the points of inflection and the intervals on which f of x is equal to 3x to the 5th, there it is, 3x to the 5th minus 5x to the 4th plus 1 is concave up and concave down. Okay? So it says find the points of inflection. How are we going to find the points of inflection? You take your second derivative. Critical points, you take your first derivative. Points of inflection, you take the second derivative. Okay? So we've got to first do a first derivative. So let's do that first. Alpha prime of x is equal to what? (15) x to the 4th minus, second, 20 x cubed. That's 0, right? That's your first derivative. Now you could go on and find out where your first root, your critical points, okay, you could do that. They didn't ask for it, so let's not. Let's go on to the second derivative. And what would that be? Positive 60 x cubed, right? Minus 60 x squared. Now, where are your potential points of inflection? Where the second derivative is equal to 0. Right? So let's solve that. What would you do? Okay, factor out 60 x squared, and what do you have left? First term, x minus second term, 1. If you factor 60x squared out of 60x squared, that goes into it one time, right? And set that equals 0. Now this has 3 possible zeros, right? But the first 2 are 0. They're a double root at 0. X equals 0 or x equals 1, right? So each of those equal to 0. This will give you x equals 0 as a double root. This will give you x equals 1 as a single root. Okay. So what we have to do is determine, we've got where the second derivative is 0, but we also have to determine whether it changes sign. The second derivative changes sign or not. So let's plug in, say, a minus 1. X equals 0 is your potential point of inflection. Okay? So let's plug in x equals, say, minus 1. You put minus 1 here, what does this produce? Negative 1 here would be a negative 1 times 60 is negative 60, right? A negative 1 here produces a positive 1 times negative 60 is again negative 60. Negative 60 minus 60 is minus 120. That's really negative, okay? Really negative, okay? So let's go to the right of 0. But we don't want to go as far as 1, so let's go to 0.5. Okay? Yeah. 0.5, I don't know if you like decimals better than fractions. Let's do the decimals. 0.5 cubed is 0.125, right? So 0.5 squared would be 0.25, and then another 0.5 turns out to be 0.125. So this would be 60 times 0.125. That's going to be something greater than 6, right? So it's greater than 6. 0.5 squared is 0.25, okay? Well, 0.25 times 60 would be something greater than 12, right? No, something greater, okay. 125 times this would be something greater than 6. 60, yeah, I said it right, something greater than 12. 0.25, in fact, a quarter, 0.25 is a quarter of 60 would be 15. So this would be a plus 6 and a minus 15, that's going to be negative. So it's negative on this side, it's negative on that side, so that means that you don't have a change of sign of your second derivative, so you don't have a point of inflection. This is concave down here, concave down everywhere. So you don't have a point of inflection at x equals 0. But the other one is where x is equal to 1. Okay? Let's do it 1. We already determined it's negative over here. Let's do a 2 in here. 2 cubed is 8. 8 times 60 is 480. 2 squared is 4. This is 4 times 60 is 240. Minus 240 plus 480. Really, really positive. So you do have a change of sign of your second derivative here, so that is a point of inflection. Your concave down here, concave up there, at x equals 1, you have a point of inflection where it changes concavity. Here, there is no change in concavity. It's concave down throughout. So sure enough, one of those produced a critical point, one did not. X equals 1 is a critical point, x equals 0 is not a critical point. Does that make sense? Yay or nay? Okay, good deal. So here's what you do. You got 3 critical points, okay? You got 2 possible points of inflection. One's at 0 and one's at 1. So they chose the same points we did, okay? they chose -1. That gave you a -120. Really, really negative. Okay? Then they did something between 0 and 1. They did 1/2. And the second root of 1/2 is still minus. Not nearly as minus, but it's still negative. So that means it's concave down coming up to 0, concave down after 0 is concave down everywhere. Okay? So therefore, there is no change of concavity, meaning there's no point of inflection. So, at 1/2 it was negative. At 2, which is something greater than 1, it's way up there at 240. Very, very positive. So it was concave down to the left of 1 and concave up, really concave up to the right of 1. So that was a point of inflection. For sure. Make sense? Okay. Are we out of time? Unfortunately, we are, aren't we? Okay. I did not mean to spend that much time on it. Homework exercises here in 4.4. Do number 1. Do any of the odds 3 through 17. And then do any of the odds 19 through 25. And then do any of the odds 27 through 39, 41 through 55. Try to do 57, and try to do 59. You can take a look at a few of the rest of those. I'll let you do it. Now, here's what I want to do next time. We just hit a little bit in 4.4. We're going to stop 4.4 and move on to 4.5 and do L'Hopital's rule. I think that's really important that you know that. So we'll do a little bit of that next time. And then we'll probably end chapter 4 there. And do a little bit in chapter 5 on Thursday. On Wednesday. Yeah. Okay.